Hi everyone, my name is Zhongyi. I'm from National University of Defense Technology. The topic I'm going to share with you today is called DeFault Mutual Information-Based Crash Triage for Massive Crashes. This is a joint work with Shandong University and the Chinese University of Hong Kong. Nowadays, fuzzing has become very powerful. As of February 2021, ClusterFuzz, the very well-known fuzzing infrastructure, has found around 29,000 bugs in Google's products and more than 26,000 bugs in over 400 open source projects. This massive amount of crashes is becoming a heavy burden for analysts. Therefore, crash triage is needed. This includes two steps: crash deduplication and fault localization. This process is imprecise, time-consuming, and labor-intensive. On the first part, crash deduplication, the goal of this step is to ease the burden on fault localization. From many crashing traces, we want to select the traces with unique crashes. So here is how this works. In step 1, we do clustering for crashes. The crashes in a cluster or in a group share the same root cause. Then in step 2, we select a unique or a representative crash from each cluster. But the challenge of crash deduplication is that accuracy and efficiency is hard to balance. This sounds contradictory. If we want this step to be accurate, then crash deduplication should be based on the result of fault localization. If we want this to be efficient, then we don't want to involve any heavy techniques, for example, fault localization techniques. From previous research, we found there are several solutions: call stack-based, constraint-based, patching-based, or crash report-based. The common weaknesses of them are, first of all, they are not applicable to general programs. They make assumptions on the settings or the environment. On the other hand, they are inaccurate. They either work at function call level or they are based on the crashing points rather than the root cause point. After deduplication, we need to locate the fault at certain basic blocks in order to facilitate program patching. There are several approaches to do so. Spectrum-based solutions use the result of test cases and their corresponding code coverage information to estimate the risk of each basic block of being faulty. Also, fault localization can be based on machine learning or program slicing. The limitation is that those approaches were unable to capture the dependency among root cause basic blocks, which causes inaccuracy on the results. In our research, we have two weapons. In site number 1, we leverage mutual information to quantify the crash relevance of basic blocks. In site number 2, we use neural networks to recover sequence information among basic blocks. So in crash deduplication, the basic blocks with the largest mutual information are considered the criterion of crash bucketing. In fault localization, first we remove the basic blocks with less mutual information, meaning that they are less relevant to the crash. This can shorten the long crashing traces. The shortened crashing traces would be suitable for the neural network to process, and the neural network is able to capture the long dependency of root cause basic blocks in the shortened traces. In information theory, mutual information is used to measure the correlation between two random variables, x and y. In our research, the mutual information is a measurement of the correlation between basic block B and crash label Y. We also use the attention mechanism of neural networks. The idea of attention mechanism is about weighing assignments on input nodes. We use this to identify the root cause of program crash by weighing each input basic block's contribution to the crash. Here is the transition function with softmax function, and the mean squared loss function is used. So we developed a tool called DeFault. It works as follows. The fuzzing infrastructure produces a large number of crashes. Those crashes are sent to the crash deduplication module. It outputs unique crashes. Each crashing trace of the unique crashes is then sent to fault localization module. The output of the tool are the root cause basic blocks. Here are the initial inputs, a set of crashing traces. In the crash deduplication module, the first thing is grouping. In round 1, we calculate the mutual information of basic blocks. The basic block with the largest mutual information is called criterion basic block. For the crashing traces that contain this criterion basic block, we group them as group 1. For the rest, we do another round of calculation and grouping. The crashing traces with this new criterion basic block is grouped as group 2. So on and so forth, until there is no crashing trace left. As long as the criterion basic block is accurate, this grouping algorithm gives no false negative, but could give false positives. Imagine that two crashing traces share the same root cause. Assume basic block BC and basic block BD are the root cause basic blocks. Basic block BC appears in trace TC, and basic block BD appears in trace TD. If the statistics of the root cause basic blocks are different, this algorithm would put the two traces, TC and TD, into two different groups. We believe this situation is tolerable in terms of crash triage. After that, we need to select a representative trace from each group. If a trace contains the criterion basic block and another basic block which is the root cause of another unique crash, then we say this trace is not representative. So the representative trace is the trace that contains the criterion basic block without root cause basic blocks of other unique crashes. In other words, crashing traces in a group may contain different criterion basic blocks. We give higher scores to the traces with more types of criterion basic blocks. The crashing trace with the least score is representative. For example, assume that the criterion basic block used for grouping of trace TA and trace TB is basic block BG. If trace TA contains criterion basic blocks Bn, Bw, Br, and Bg, and trace TB only contains criterion basic block Bg, then trace TB is the representative one. For fault localization, first of all, we use AFL fuzz to generate samples and construct a dataset. The AFL fuzz is used to mutate the crashing inputs. This would produce many non-crashing inputs that explore different paths. Then we use AFL fuzz again to mutate those non-crashing inputs. The produced traces would include a portion of basic blocks that are also included in crashing traces, but those basic blocks are irrelevant to the crash. This makes statistical characteristics of the produced traces significantly different from that of the crashing traces in the dataset, which is the key to the success of subsequent steps. However, the execution traces are too long and cannot be directly fed into the neural network. To this end, we leverage mutual information again to filter out irrelevant program components. We define the ratio of a function's mutual information to label y's entropy as the function fi's contribution to label y. First, we filter out irrelevant functions if the ratio is smaller than 0.5. Similarly, for a basic block, if its ratio is smaller than 0.8, we remove it from the trace. Those two values are empirically set. With the shortened traces, we send them to the neural network encoding with one-hot vectors. The length of the neural network is set to the length of the longest trace. The short inputs are padded with zeros. The output is 1 or 0, meaning that it triggers crash or not. The network structure is the classic LSTM network with the attention mechanism. The output of the LSTM layers is defined like this. Each element is related to previous elements. Then we send the output of LSTM to softmax layers and have the relevance score of the elements. Then the relevance score is multiplied with the input and sent to fully connected layers. The trend network indicates a relevance vector for each sample. In this step, we want to have a set of root cause basic blocks. In other words, we need to categorize basic blocks into two groups. Group 1 are the root cause basic blocks. Group 2 are the rest. So, for successful categorization, the sum of the variances of two groups is the smallest. On this condition, we output the group of basic blocks with higher relevance scores. We evaluated this tool with 20 programs, including 8 CGC programs and 12 real-world programs. Those programs are chosen from different categories and have known crashes. We reproduce the crashes using AFL fast, which generates a total number of 22,216 crashes. The network is trained using TensorFlow and Keras. The ADAM optimizer is used with an initial rate of 10 to the exponential of -6. The training stops when either the fitting rate becomes 99% or the iteration round equals to 100. We manually examine the root cause of the known crashes for the ground truth of fault localization. After examining the root cause, we manually write the constraints of crash triggering and use scripts to automatically determine whether the crashing inputs satisfy the constraints. This is used for the ground truth of crash deduplication. For crash deduplication, we compare our tool with the semantic crash bucketing tool, FL-Father's deduplicator, and Home-Father's deduplicator. SCB uses patching-based bucketing techniques and only works for buffer overflow and null pointer dereference. FL uses hash of crashing paths to do bucketing. Home-Fuzz uses hash of call stack to do bucketing. Regarding accuracy of crash deduplication, DeFault reports no false negatives. So do SCB and AFL. HomeFast reports one case where two root causes are within the same function. For false positives, DeFault gives less false positives on 19 cases when compared with other tools. For the cases where DeFault gives false positives, some use after free vulnerabilities are triggered but not lead to any crash, which makes the prediction of criterion basic blocks inaccurate. In terms of performance of crash deduplication, DeFault is super fast. The time to process each program is 19 seconds on average. The main reason is that DeFault analyzes the statistics of basic blocks, and the computation of mutual information values only involves some of the basic blocks. The values of mutual information are stored and indexed from hash tables. This does not involve heavy techniques. As such, it takes much less time for DeFault. For fault localization, we compare DeFault with Aurora. Aurora analyzes the statistics of execution paths and outputs suspiciousness score. False positives occur in the presence of use-after-free vulnerabilities. When there is no memory operation on the piece of memory that is freed, no crash would be triggered. The behaviors of the root cause and that of the crash point are the same, which leads to inaccurate labeling for some samples. For this step, there is no false negative reported. The performance of DeFault is relatively good. On average, the time cost of DeFault to locate each root cause is about 37 minutes. There are some limitations about this work. Accurate identification of criterion basic blocks is critical. If the identification of criterion basic block is inaccurate, DeFault can give false positives and false negatives, although no false negative is reported in the experiments. That is all. Thank you for listening. This project can be accessed by this link. Please drop me an email for further questions.